So I want you to think about what we mean by amplitude, crest, and wavelength. Okay, so I'll give you a couple of minutes to have a think about that, and then I'll pick on some people. You don't have to write anything down, but if you feel like it might help you if I pick on you, then feel free to write something down. Right, okay, amplitude. Craig. Yeah, the height of the wave from the centre line. Yeah, excellent. What about crest? Sorry. Yep, top of the wave. And wavelength, probably the most difficult one to explain. Go on, Harris. Yep, so the easiest way to describe it is the length from one crest to the next crest. But you can say from one point on the wave to the same point on the next wave. So wavelength is the length of one wave. Okay, right. So we're on to, let's go back onto our booklets. I think we're on page 6 of the booklet. Should be speed of sound. Should look like that. Okay, so in the previous lesson, we talked about how to define parts of a wave, so things like wavelength, amplitude, crest, trough, and we also just looked at what longitudinal and transverse waves are. Okay, remember, the only longitudinal wave you need to know is sound wave. So what I have on my front desk is an experiment to measure the speed of sound. Okay, so what it is it's called a sound switch. It's basically a microphone. Okay, and another one over here. And at the moment they're a meter apart. Okay, so what I'm going to do is I'm going to make a quite sharp sound because it picks up that better. So something like this. Yeah, and I'm going to make it in front of this first microphone. So when that microphone detects the sound, it starts timing. And then when this microphone detects the sound, it stops timing. And I know you might think, well, don't they just both detect at the same time? Not quite. There is a difference. Okay, so there's a difference between where this detects the sound and this detects the sound. It's quite small, very small, but there is a difference. Okay, because sound has to travel. We know that sound has to vibrate and pass on its energy in the air particles. Okay, so that is basically what this experiment is. And what we do is we change the distance and we measure the time. So we'll make the distance smaller, and then we'll measure the time it takes to go from one to the next step. Okay, and then we can work out the speed of sound from those values by just doing our normal speed equation. Remember the speed equation? Speed equals, yep. Okay, so for the speed of sound, we need to do distance divided by time. Okay, and the time will probably be in milliseconds, so times 10 to the minus 3 or divide by 1,000. Okay, so the first one we'll do is we'll just take the 1 meter because it's easier that way. So 2.97 milliseconds. So distance travelled 1 meter, time taken 2.97 times 10 to the minus 3 seconds. So we'll do let's go so 0.75 meters. Do you think it's going to take more time or less time? Yeah, it's got less force to travel. 2.12 times 10 to the minus 3. Next one I'll go for is half a meter, so 0.5. 1.41. That's quite good, isn't it? And let's go for 0.25. The smaller the distance, the more sort of errors we get in, because we end up getting sort of, they start picking it up at very similar times. So we'll see how this one goes. 0.67. Right, so I want you guys to use the speed equation. Speed is distance divided by time, so distance in meters, time in seconds. So work out the speed of sound for each one of those, and the average. We're all happy with calculating averages? Add them all up, then divide them by the amount that there are, so in this case it'll be 4. Have a go at that and I'll do it as well, and we'll see if we get to the same answers. Remember, if you're struggling with using your calculator, please let me know. You okay at the back? Okay, so you're working out the speeds? Yeah, I think do round it to the nearest whole number. It makes life a bit easier. Your speed of sound, yeah. So that's what I got. The last one in the table, 373. Have you tried pressing it? Oh, okay. What does it tell you on the? Okay. Right, are we all getting similar answers to me? Okay. So I found the average to be 355 meters per second. So that would be my conclusion. The speed of sound was found to be 355 meters per second. Have you seen meters per second written down like that before? Some people yes, some people no. It's literally just another way of writing down m/s. The only reason that we start using that now as we get into National 5 is because that slash can sometimes get mixed up with ones or i's and things like that. So it's just easier to do. So s minus 1 is m over s. We've done fractions and yet. So really, it's just another way of writing that. It doesn't matter if you write that or that. Really. It's just a different way of writing it. You don't have to do anything with your calculator. You don't have to put any power of -1 in. That's what it actually is. The actual value is, yeah. But the one that we calculated is 355. Yeah. Yeah. So you want to round it. So basically, the rule is round it to the same amount that's in the question. So if you're in an exam and the question was just rounding it to the nearest whole number, you do that. If you were in an exam and the question gave you 0.34, then it would be 2 decimal places. So it's the same as the question. Yeah. Everyone got that done? So the speed of sound was found to be 355 meters per second, but in reality it's 340 meters per second. So that's not actually too bad a value. Okay, leave that up for a second. Has everyone got that? Okay. The next page I'm going to skip for a second because it's going to be your homework. We might get round to starting it later. So we'll skip that for a second. And we're going to move on to experiment to see sound. Now, this page, again, if you were here in first year, it's probably the exact same page that you would have seen in your first year sound booklets. But we'll go through it anyway. So basically, this is if you're using an oscilloscope. Has everybody seen an oscilloscope before? Definitely saw one in first year. Yeah. There would be, yeah. It basically looks like, gives you a screen like that. Yeah, that's an oscilloscope. I'll get one out again for next lesson as well. So, in a telephone, speech patterns are converted to electrical signals. The signals travel through the wires very quickly at almost the speed of light. And the mouthpiece of a telephone contains a microphone and the earpiece contains a loudspeaker. So in the microphone, what is the energy change in a microphone? Yes. Yep, good, you got it the right way around. So you speak into a microphone, so it starts off sound energy, and it changes into signals, so electrical energy. And in the loudspeaker, it's the opposite way around, so it's electrical to sound energy. It takes those signals and it produces a sound. Anyone have a guess at the wires? It's a tricky one. Yeah. Excellent, yes. So electrical energy, and it makes the sort of electrons move, so kinetic energy. Okay, so as I said, it's not particularly great from the front if I just have an oscilloscope at the front, but I'll get another one. I'll request it for next lesson in case anyone hasn't seen an oscilloscope. But we're going to look at a video recording of an oscilloscope. So, oscilloscope and signal generator. Okay, and the results, this is just a normal trace. Okay, so that's in case we just had a particular sound. Okay, so the first one says effect of volume. So it says add a second line to the diagram to show how the trace is affected when the volume increases. I think most of you can probably guess already because you've sort of seen this before, but I have got the film of it. So yeah. So this is volume. Oh no, that's not volume, that's pitch. Let's go back. It's this. That's high, low and high notes. Nope, that's also pitch. I'm sure I had one. Anyway, let's try this one again. Oh, it does it. Yeah, it does it briefly. So let's go back to the beginning. So it starts off with quiet, and then it increases the volume there, and then it does again with a different note. So that's quiet, increasing the volume. Okay, so what's happening when you increase the volume to the wave? Yeah, increase. Yeah, it makes the crest higher. So go back to here. The effect of volume. So you might want to get a different color if you can. Add a second line to the diagram to show how the trace is affected when the volume is increased. So you want it to stay the same width, but get taller, basically. So what is increasing? The amplitude is increasing. Okay. And so the next one is pitch. So this one actually is pitch. So let's go back. Okay, so it's going higher in pitch, and we're seeing there's more and more waves on that screen. Okay, so the width is actually getting smaller. So if we go back here again, the effective pitch. So we want the same height this time, but we want more waves. So make sure it's the same height, but sort of thinner waves. The frequency is increasing. There's more waves per second. And the last one, effective volume and pitch. It means you can basically go crazy. So it can be taller and they can be thinner. There you go. So amplitude and frequency increase. And the last video that I want to show you is just remember last lesson we went through and we changed the signal so who could hear what. Well, I've got an actual oscilloscope trace of that, so you'll be able to see the waves change. Okay. So if you have a look here, this one's the 20 to 20,000 hertz video. Yeah. So just start here right there. What is what happens there? So some oscilloscopes just repeat it, like bounce it back off each other. Yeah. Like you have to keep changing the settings when you're using an oscilloscope, otherwise they just sort of disappear because there's too many of them. Right. So we'll pause it there. But you can see how the frequency is getting, well, the frequency is increasing. There's more and more waves on the screen. Yeah. So as it gets higher pitch, you get more waves. Remember, frequency is the amount of waves that pass in a certain amount of time. Right. So